Hello and welcome to the AI Affairs podcast. Today, we're diving deep into perhaps the most fascinating development in AI right now. It's this shift from systems that just predict the next word or recognize a pattern, to those that are actually building sophisticated internal simulations of reality. Researchers are calling these world models, or WMs.
And it's a really profound shift. This isn't just some technical upgrade. We're talking about AI learning the fundamental laws of existence, essentially.
Exactly. Intelligence that's actually becoming grounded.
Yeah, if the last decade was maybe about teaching machines to understand data, this one feels like it's about teaching machines to anticipate reality. So our mission today really is to unpack this cutting edge. We'll look at three pretty distinct fields where these WMs are making massive strides.
Okay, where are we starting?
First, physical robotics and embodied AI. Then we'll jump into scientific simulators, think huge problems like protein folding and climate science.
Oh, wow. Okay, big scale.
And finally, we'll land on modeling human psychology and behavior. It's quite a range of applications.
It really is. And we want to help you, the listener, understand what connects all these seemingly different areas together. Okay, let's unpack this. Where do we begin? The physical world.
Let's start there. With the physical world where, the rubber literally meets the road, embodied artificial intelligence, or EAI.
Right, EAI. I've heard that term. It's not exactly new, is it?
Yeah.
Didn't Turing talk about something like this?
He did, yeah. Way back in 1950, his embodied Turing test concept. The basic idea is pretty simple, really. You've got disembodied AI, that's AI solving abstract digital problems like scheduling or maybe language translation.
Things happening purely on a computer.
Exactly. But embodied AI actually interacts with the physical world. Think drones, manufacturing robots, self-driving cars eventually.
Got it. Things that move and sense in the real world.
And for that physical interaction to work, for the robot to, move, sense, react properly, it really needs a closed loop. The sources consistently point to three necessary components for this loop.
Okay, what are they?
First, active perception. That's basically using sensors, cameras, LiDAR, whatever, to continuously observe the environment, what's out there.
Makes sense. You need eyes and ears.
Second, embodied cognition. This is the tricky part. It's where the agent updates its internal understanding based on its actual experiences. Learning from doing, essentially.
Okay, learning from interaction. And
Third is dynamic interaction. This is the action part, how the agent controls its actuators, its motors, its grippers to actually move or manipulate things in the world.
Perception, cognition, action, the loop.
The loop, yeah.
Now, it feels like large language models, LLMs, were sort of meant to tackle that middle part, the cognition bit, right? They're amazing at reasoning, planning.
They are absolutely brilliant at semantic reasoning and task decomposition. You can give them a high-level, maybe slightly fuzzy instruction like, hey, tidy up this workspace.
Yeah, something a human would say.
Exactly. And frameworks like Saycan show they could break that down into a sequence of discrete actions. Go here, pick that up, put it there. Very powerful for planning.
But there's a catch, isn't there? That's where this gets really interesting, you mentioned.
There's a huge catch. LLMs often fail, quite spectacularly sometimes, to ground those planned actions in, physics, in reality.
How so?
They might suggest a sequence of moves that looks perfect on paper or in a text simulation, but completely ignores friction or gravity or the fact that an object is heavier than it looks or that the shelf it wants to put something on is already full.
Ah, so they know the words for physics maybe, but not the actual constraints.
Exactly. They rely fundamentally on static, pre-trained knowledge from all the text and data they ingested. They haven't experienced physics. They lack that real-time adaptation you get from interacting with the world.
So the robot needs more than just a planner. It needs like an internal physics engine, a sandbox.
That's a great way to put it, an internal mental sandbox. That's essentially what a world model provides in this context.
Okay, tell me more about these world models.
WMs are crucial here. They build these internal representations of the environment and, critically, make future predictions about how things will behave if certain actions are taken, predictions that comply with physical laws.
So they let the robot think, if I push this box, will it slide or tip over? Before it actually pushes.
Precisely. They help the robot reason about not just what exists around it, but how things behave. It's like the WM is the engineer double-checking the LLM's clever plan, making sure it won't, fall apart in the real world.
Okay, so the LLM provides the high-level goal, the what, and the WM provides the grounded simulation, the how.
You got it. And the sources really emphasize this synergy. They call it the Joint Multimodal LLM, MLLM. WM-driven architecture. It's seen as the necessary path forward.
MLLMWM. Got it.
Yeah, the MLLM handles the high-level context, the semantics, the what and why.
Mhm.
The WM handles the physics-aware simulation, the how and when. Systems like Evo Agent are examples trying to implement this.
So it bridges language understanding with actual physical understanding, trying to get towards general physical intelligence.
That's the goal. True self-reflection about physical actions and consequences. Without that WM, the LLM is sort of just talking to itself, planning in a vacuum.
Okay, that makes a lot of sense for robotics, grounding the intelligence. Now, you mentioned we'd shift focus pretty drastically.
Right. Let's move from controlling a single robot in a room to these high-stakes scientific modeling challenges, where AI is building essentially digital twins of vast, complex natural systems.
And first step is protein folding.
AlphaFold.
AlphaFold, yes.
Yeah.
An incredible, truly landmark example of a scientific world model. For, over 50 years, predicting the 3D structure of a protein just from its amino acid sequence was this holy grail of biology.
Right. Hugely complex problem.
And AlphaFold basically solved it. It achieved near experimental accuracy. It was stunning.
I remember the headlines. And the accuracy numbers were just wild, weren't they?
They really were. The specific detail that always sticks with me is the median backbone accuracy, 0.96 angstroms RMSD.
Okay, translate angstroms for me again. Tiny. Incredibly tiny. 1/10,000,000th of a meter. So we're talking about predicting the position of atoms with precision that's genuinely competitive with doing the actual painstaking experiments in a lab.
How does it even do that? What's the world model part here? Is it simulating physics again?
It's simulating the consequences of physics and evolution, you could say. The architecture is really sophisticated. It's not just throwing data at the wall. At its core is this novel component they call the evoformer.
Evoformer.
So instead of just looking at the protein sequence itself, the evoformer processes two crucial streams of information together. First, multiple sequence alignments, or MSAs. That's basically looking at how this protein or similar ones have changed across different species over evolutionary time.
So learning from evolution's trial and error.
Exactly.
Yeah.
And second, it looks at pairwise residue features, essentially geometric information about which parts of the protein chain are likely to be close to each other in the final folded structure.
Geometry and evolution combined.
Combined and processed iteratively. The system sort of forms a structural hypothesis early on and then keeps refining it, using both types of information to guide the folding process in simulation.
And the payoff isn't just accuracy, it's speed, right?
Oh, massively. That's the computational value. AlphaFold generates these highly accurate predictions in GPU minutes or hours. The experimental methods, they can take months, sometimes years, and cost a fortune.
So it's completely changing how things like drug discovery can be done.
Fundamentally, you can screen potential drug targets or understand disease mechanisms at a scale and speed that was just unimaginable before.
Incredible. So we've gone from robot physics to molecular physics. Now you said planetary scale.
Yeah, let's zoom all the way out. From angstroms to the entire atmosphere. We're talking about neural general circulation models or neural GCM.
Okay, GCMs are the standard climate models, right? Massive simulations.
Traditionally, yes. Huge, complex codes running on the world's biggest supercomputers, solving millions of explicit physics equations for fluid dynamics, radiation, etc. Neural GCM is different. It's a hybrid approach.
Hybrid, meaning it mixes AI with the traditional physics.
Exactly. It's what they call a differentiable hybrid GCM. That differentiable part is key.
Why differentiable? What does that enable?
It means the model can learn and be optimized using the techniques common in machine learning, like backpropagation. So it has two main parts. First, a dynamical core that still solves the fundamental equations for large-scale fluid motion, the big atmospheric flows. But this core is designed to be differentiable.
Okay, so the physics part is learnable in a way.
Parts of it, yes, or at least the AI can learn from it more directly. The second part is a learned physics module. This is a neural network designed to handle all the really complex, messy, smaller-scale processes that traditional models struggle to resolve explicitly, things like cloud formation, precipitation, turbulence.
Stuff that's hard to write exact equations for.
Precisely. The neural network learns to approximate those effects based on the larger-scale conditions provided by the dynamical core.
And the big benefit here, you mentioned accessibility and speed.
Immense benefits there. This hybrid approach achieves orders of magnitude computational savings. We're talking about running reasonably complex climate and weather simulations on a high-end laptop instead of needing dedicated time on a national supercomputer.
That's huge. It democratizes the whole field.
Completely. Researchers anywhere, potentially, could run meaningful climate simulations or weather forecasts.
But what about accuracy? Does this speed come at the cost of quality compared to those giant physics-only models?
That's the crucial question, isn't it? And the results are really promising. For medium-range weather forecasting, say, up to 15 days, neural GCM is competitive with the state-of-the-art physics-based models.
Okay, so for weather, it holds its own. What about long-term climate? That seems harder.
It is harder, especially stability. Many early AI weather models looked good short-term, but then, well, they'd blow up numerically if you tried to run them for years or decades. But neural GCM demonstrates stability for these decadal climate simulations.
It doesn't crash and burn.
Right. And critically, it accurately simulates emergent long-term phenomena. Things like realistic seasonal cycles, plausible El Niño patterns, even the tracks and intensity distributions of tropical cyclones seem realistic. It suggests learning the short-term physics can translate to capturing long-term climate behavior.
So we've got AI grounded in robotics, simulating molecules, simulating the entire atmosphere. Where does it go next? You mentioned human behavior.
Yes. Let's bring the concept of world models, or perhaps more accurately, behavioral models, into the human realm. This is about simulating users, maybe for things like UX testing or market research, using what are often called digital twins or synthetic users.
Okay, digital twins, synthetic users, are they the same thing?
Similar concepts, but a key distinction the sources make. Digital twins usually aim to simulate specific individual users. Often, they're built using quite detailed data about that particular person.
Like my own personal digital twin?
Potentially, yeah. Whereas synthetic users are generally designed to mimic broader user groups or population segments. They're typically based on more generalized demographic, date, age, location, maybe some stated preferences.
So individual versus group simulation, how well do they actually work?
Well, there's some interesting studies. One look at digital twins built just from survey data for specific people. They found these twins were pretty good, about 78% accurate, at predicting how that same person would answer other questions on the same survey that were perhaps missing.
Okay, good for filling in gaps in existing data.
Right, useful for handling survey attrition, maybe. But when they asked a digital twin completely new questions outside the original survey scope, the accuracy dropped significantly, down to about 67%.
So they struggle to extrapolate, to generalize beyond what they were explicitly trained on.
That seems to be the limitation, yes. It suggests that just having survey answers isn't enough context. They need deeper grounding in that person's world.
Which points towards needing richer data, right? Like maybe interview transcripts.
Exactly. And that leads directly to study two. This was fascinating. They created interview-based digital twins, and the method was surprisingly simple. They basically just augmented the prompt given to a large language model with the full transcript of a detailed qualitative interview with the person.
So no complex model retraining, just giving the LLM the person's actual words and stories as context.
Pretty much. They grounded the model not just in abstract demographics, but in the person's narrative, their expressed experiences, their reasoning.
And how did those twins perform?
Impressively well. They achieved around 80–85% accuracy on predicting survey responses, consistently outperforming models that only had demographic information. It suggests that the richness of qualitative contextual data is incredibly powerful. The simplest method, giving it rich context, yielded the best results.
That makes intuitive sense. But when we're simulating humans, there's always the elephant in the room. Bias. Algorithmic fairness. Did feeding them richer data help with that?
That's maybe the most critical finding. Yes, it did, significantly.
Yeah.
The study found that the interview-based twins showed much lower bias across sensitive attributes like political ideology and race compared to the models relying only on demographics.
Really? How much lower?
For political bias, the reduction was somewhere between 36% and 62%. That's substantial.
Why would that be?
Well, think about it. If you only give the model broad demographic categories, middle-aged suburban voter, say it's almost forced to rely on stereotypes associated with that group to make predictions. But if you give it that person's actual words, their specific reasoning, their unique experiences from an interview.
It can make prediction based on the individual, not the group stereotype?
Exactly. It allows for more nuanced, individualized, and ultimately more equitable predictions. Rich context seems to fight bias in this case.
That's a really hopeful finding. But what about the other approach, the synthetic users based just on demographics? You said they had flaws.
They did. Study 3 looked closely at these synthetic user populations. The problem wasn't necessarily that they got the average opinion wrong. They often captured the general trends reasonably well.
Okay, so what was the flaw?
The flaw was in the variability. They failed to capture the true spread, the diversity of opinions, the magnitude of effects you see in real human populations.
Meaning?
Meaning their simulated responses tended to cluster too closely around the average. They showed consistently lower standard deviation than the real human data. They missed the outliers, the strong opinions, the edge cases.
And those outliers can be really important, right? In markets and politics.
Absolutely. If you're only simulating the average Joe, you might miss the early adopters, the vocal critics, the people driving change. You get a smoothed out, less realistic picture of the population's actual dynamics.
So the big takeaway across all these human simulation models seems to be context, context, context.
It really is. Accuracy, fairness, realism, it all seems to hinge on the depth and richness of the contextual information you provide to the model. You need to ground the simulation in realistic detail, whether that detail is about the physics of a robot's environment or the nuances of a person's lived experience.
Okay, so stepping back and looking at everything we've covered.
Yeah, let's do a quick recap. We've really tracked this idea of grounded intelligence across different scales. We started with robotics, seeing the need for that joint MLLM-WM architecture to connect language planning with physical reality.
Right, the planner and the simulator working together.
Then we saw AlphaFold using evolutionary and geometric context, its version of a world model, to predict protein structures with incredible accuracy.
The Evo former block, yeah.
Then neural GCM, using that hybrid differentiable physics ML approach to build stable, efficient climate models by learning the unresolved physics.
Bringing climate modeling to the laptop level.
Yeah. And finally, with human behavioral modeling, we saw just how critical deep, qualitative, contextual data is for creating digital twins that are not only accurate, but also less biased than purely demographic models.
It really feels like the unifying thread is AI building these internal, grounded models of how things work, whether it's physics or psychology.
That's the core idea, moving beyond pattern matching to genuine simulation and prediction based on underlying principles.
So what does all this mean for you, the listener, especially thinking about how these incredibly powerful systems might actually get deployed out in the real world?
Well, it means these advanced systems need equally advanced operational support. It's one thing to run AlphaFold in a data center or neural GCM on a powerful laptop. It's another thing entirely to run something like that Evo agent with its complex MLLM and WM on a robot in a warehouse or on a drone operating out in the field.
Right. The computational demands must be huge, and the hardware out there is often limited, right? Battery power, processing constraints.
Exactly. So future success, especially for embodied AI operating in dynamic real-world environments, depends heavily on hardware optimization. We need ways to make these powerful models run efficiently under really strict latency and power budgets.
How do we do that? Shrink the models.
That's a big part of it. Techniques like hardware-aware model compression, things like quantization, which uses lower precision numbers, or pruning, which removes less important connections in the neural network, and also hardware-software co-design, developing chips and algorithms together, specifically for these kinds of AI tasks.
So making sure the brain fits efficiently into the body, basically.
That's a good analogy, yeah. Ensuring these complex world models, capable of simulating intricate physics and behavior, can actually execute in real time on the limited resources available at the edge, on the device itself.
Which leads us to a final thought, perhaps. As these AI systems become increasingly our primary tools for scientific discovery, for prediction, maybe even for understanding ourselves,
We have to keep asking critical questions, don't we? What is the computational cost of simulating our world at these different levels of fidelity? And maybe more importantly, how much accuracy, how much richness are we willing to trade for speed, efficiency, and the ability to deploy these powerful simulations everywhere?
a fascinating trade-off to consider. How much reality can we afford to compute? Thank you for listening, and see you next time on AI Affairs.